Cool, so thanks. I'm Philip, and I work on the package security team at GitHub. And we've spent the last year working on adding build provenance to the NPM registry. So kind of here to talk about a bit why we did that and how that could look like for other package registries. And I know provenance has been mentioned a few times, but just to kind of describe it again, what I mean by that in this context is really capturing information about what happened before the package ended up on the registry. So where did it come from? Who made it? How was it made? And a bit of background, kind of personal background. The reason I got interested in this supply chain security space was that I used to work on Dependabot. And most of you who use GitHub are probably aware of Dependabot. Let's just say it's a useful bot if you don't have too many dependencies. But a kind of core design feature of Dependabot is to keep you up to date with the latest version of your dependencies. And this turns out to be a good strategy if you want to avoid accidental vulnerabilities. So vulnerabilities that are checked into code and maybe not immediately noticed, and then someone finds it, and there's a security advisory, and it gets patched. So usually the latest version will be the best version to be on. But it's really not great for these kind of deliberate supply chain attacks that we've heard a few times that are massively on the rise. So for example, when a dependency, an attacker takes over a popular dependency and publishes a new malicious version of that dependency, being on the latest version is really not what you want. So this got me motivated to try and work on this problem. And it's like you kind of solve one problem and you realize you've kind of created another problem, so you try and solve that one. So let's just talk about why build provenance and how does it try to solve this problem. For me, it really comes down to transparency and trust in open source code. And I feel like there's a lot of solutions that are kind of converging in the same space, and I think they kind of complement each other really nicely. So we know that a lot of these attacks that happen on dependencies being taken over, they don't happen by an attacker compromising the source code repository. It happens, but it's relatively rare. And it's just getting harder with the more kind of protections that are in place, two-factor authentication, enforcements, branch protections, all these things. And really, we want to get to a place where we know we can trust, OK, we have these controls, and the final package that ends up on the registries actually comes from that source code that I've spent time protecting. And a lot of these attacks happen because an attacker has compromised some step between the source code and the package ending up on the registry. So either stealing some credentials or compromising a build. And we really want more transparency into this process. And I think, yeah, so there's loads of solutions here that are being discussed already, like rebuilding packages, OIDC authenticated publishing, and the kind of BYOB, like SLSA builders. They harden all of these things, and I think kind of together we can get a really, really solid foundation. So what are some of the requirements that we need to bring build provenance to a package registry? So we need some way of verifiably kind of linking or binding a package to where it came from, so the kind of build source or the source build. And we need to support kind of at-scale distributed signing and verification. So package registries by nature support multiple maintainers, many consumers. So it's a kind of distributed problem. And I think for any security solution to really be successful and gain adoption, it needs to provide a seamless developer experience, or as kind of close to enabled with safe defaults as possible. So how does this look like for NPM? So I'm going to use NPM as an example, and then I'm going to break this down and talk about how this could look like for another registry and what's kind of involved, what the work is. So here, in this blue box, we basically have the cloud CI/CD provider ensure the source and the build instructions that were used to build the package. And it provides this information in a signed OIDC ID token that William already talked about. So we can kind of get these follow-on benefits by building on these open standards. And these build properties are then sent to Sigstore, which really enables signing without maintainers having to manage keys, and then us having to establish which keys belong to what identities. And then we also get Sigstore also provides a public ledger for auditing purposes. And then we take this signed attestation and we send it to the registry for later verification and kind of to be able to surface that information to users. So notice that we're not trying to bind a package to a human identity. Instead, we're binding it to code. And I'm kind of thinking of the source code or the build source as the identity, so that we can start to treat that as the canonical source of truth. Like, I want to put in place all these controls around it. I want to trust that that's actually the thing that ends up in the package, and then later verify that it hasn't been tampered with. We're also saying that really open source packages should in some way be built and published in the open so that we can audit that process and establish trust. And then this is maybe like the slightly controversial point, but we can scale this signing and verification by trusting a few systems. And by doing that, we can then kind of automatically verify signatures produced by those systems, or packages signed on those systems. And this really boils down to for provenance claims to actually have strong security guarantees, we need some, there are some requirements on the build system to actually make that happen. So we need a build system that actually runs in an isolated ephemeral environment, so that individual builds can't influence each other or impersonate each other somehow. But really the key point here is that the build system needs to be able to securely communicate this provenance information to the registry without a build run being able to tamper with that information or kind of falsify it or impersonate some other package. And these requirements mean that you can't produce provenance from anywhere. That you won't be able to do it from your personal development machine. And today, this means that builds need to happen on cloud CI/CD systems that have these properties or can make these kind of provenance claims that we can verify. And William already touched on this. We're just drilling into this a little bit more. So we're using the OpenID Connect ID token as the kind of machine identity to bind the package to the source and build. And it gives us exactly what we need for the build to be able to securely communicate this information to the registry without an individual build being able to tamper with that information. But the actual token itself, and I think William alluded to this, it's not designed to be long-lived or even publicly shared, because it can include all this PII information. So it's not a good medium for actually storing it in the registry and then using it for later verification. So we need some other medium. And this is where Sigstore comes in. And I think the killer feature of Sigstore, in my opinion, is its ability to bind one of these OpenID Connect identities or machine identities. It can also bind email identities, but for our purposes, it can bind this machine identity to a kind of throwaway signing key, and using a X509 signing certificate. So this is the same standard used to secure web traffic, but in this case, the users is scoped to just code signing. And certificates are designed to be publicly shared and verified at a later date. So this is a much more suitable medium to store for long term. Registries host packages that are many, many years old, so we need to be able to verify things long after the fact. And as a kind of aside, you might be wondering, like, okay, how do I trust Sigstore? And this is where Tough comes in for Sigstore. Won't go into too much detail, but Sigstore uses Tough in a more limited fashion to some of the talks yesterday, where it's just used to securely distribute the certificates and signing keys to the client, so it can then establish trust and verify that, yes, Sigstore actually signed this certificate, they actually received this signature, and saw it at a particular time. And it means that there's a great kind of revocation story that if Sigstore is compromised, a client would immediately know. So let's go back to this overview of how NPM build provenance works and just break this down. So I want to break it down into 3 sections, give you a clear idea of how this would look like for another package registry. So we've got this step in the blue box where we're kind of collecting the provenance information and then signing it. We have the registry that needs to actually receive these provenance attestations, verify them, and then store them. And then not on this slide, but we also want to supply users with this information, both for verification and then also to make more informed decisions about whether to trust a particular package or not. So we know we want to collect this provenance information, and I love that all the talks before have kind of been building up to this. And the actual ID token itself is not a great, both not a great medium to store for later verification, but it's also, there's no standard between CI/CD systems what claims to put in there and in what format. So we want a standardized format to collect this information, and the SLSA spec was created exactly for this purpose, and it's what we're using in NPM. And we recommend that you would build this functionality into the package manager CLI itself. This is what we've done for NPM. But I've created this little CLI tool just to demonstrate this particular step. So you can run on GitHub Actions and GitLab, and it will collect this provenance information and spit out an unsigned provenance, SLSA provenance statement. And for NPM, we set the subject of this provenance statement to the package, and the digest matches the tarball so that we can then verify that they link together. And then once you have generated this provenance statement, you want to sign it, and this is where the Sigstore client comes in. So the same as before, like ideally you'd then build this into the NPM, or into the CLI, package manager CLI itself. But you could also use the Sigstore node client, for example. So here we're attesting the provenance statement that we just generated. And if you run this on GitHub Actions or GitLab, it will do this whole dance behind the scenes where it requests an ID token, sends it to Falsio, it gets a signing certificate, it signs the package, and it also creates the actual keys that it uses, but these are throwaway, ephemeral. So once it's done, it's signing, it throws away the private key. The public key is embedded in the signing certificate. It also uploads proof to the Sigstore ledger service Recall. And then you get this offline verifiable Sigstore bundle as an output. And there's a kind of asterisk around the offline because you still need to fetch the latest set of keys from Sigstore using a tough client. But this bundle is it's a perfect fit for like long-term storage. So this is what we upload to the registry, along with the package and the tarball and all the metadata. And then the registry side, before actually accepting the package, we want to do some validations. We want to make sure that the provenance was indeed signed by Sigstore. It's just not something falsified. For NPM, we also ensure that the build source was public at the time of signing, and that the hosted runner was used to ensure that builds are ephemeral and isolated. We also, because by default in NPM, we wanted the default kind of experience to be as seamless as possible. So really, if you're already publishing on actions, the only thing you need to do is add -- provenance and make sure that the workflow can request an ID token. Hopefully, we can get rid of that permission step in the future. But this means the build can still influence the generated SLSA statement. So we server-side ensure that the generated SLSA statement matches the signing certificate, which comes from the ID token, which the build can't influence. So I think I have some ideas of how we could improve this longer term, but this is what we went with currently. And then, because it's all built on SLSA and common standards, you can then also optionally use a SLSA builder to generate the provenance and just attach it to the npm publish command instead of asking it to do the generation. And then once you've verified the provenance and whatever policies you want to have in place, you want to also actually attest that the registry accepted the package. So this commonly implemented as a kind of registry side signature. But for NPM, we've also actually done this with Sigstore, so we upload proof to Recall, the transparency log, that NPM accepted a particular package and version. And this can help keep the registry honest. So if the registry starts to re-sign packages, it could be detected. And so the output of this is that you now have 2 attestations per package and version, and we want to store these somewhere for later retrieval. And this could just be a simple blob storage, so you can then just query by package name version or the digest of the package. And then kind of once you've done all of this, like really the payoff is in providing users with this information so that they can make more informed risk assessments. Because having provenance itself it doesn't mean that the package is immediately trustworthy. It doesn't mean that it's not free of malware or something like this. It just means that there's this verifiable link back to the build source, and then you can go and audit that, and then kind of build policies around that and trust that. And it means that you can audit that maybe once or periodically, and then you don't need to audit it every single time there's a new version if that chain is the same. And we also recommend you want to provide some kind of programmatic access. Or I guess I skipped over this. So yeah, you want to have some UI that gives people these links so they can follow. You also want to provide some programmatic access. Probably will also power the CLI, but it can also power tools like the SLSA verifier, which currently works with NPM provenance. So this is a really cool example of how all these things are kind of building on each other. And then you will extend the actual package manager CLI tool to be able to verify these attestations for install dependencies. This is something we haven't done for NPM yet, is build more powerful verification policies. So ideally, we get to a place where you can actually start creating policies of what is the expected source for a given package and lock that in. And it would, maybe optionally, you can configure it to just blow up or ask if it changes. And just quickly on the UI side, this is how it looks for NPM package that has provenance. We link to the build summary and the source commit and the build file. And then you can also look at the entry on the public record log. And the other thing that we've done is we periodically check that the source is still public. And if it isn't, we kind of treat it as, we kind of say that the provenance is no longer trustworthy, and you should probably make your own choice whether to trust it. And we will show a big red warning banner around it. And so just in summary, the goal of build provenance is to have packages be transparent about their contents and how they were built, so that we can anchor trust in the source code. And by building in the open on trusted CI/CD systems, we get this nice property where we can automatically verify packages produced by these systems. And just to kind of close off, this is my kind of vision for how we can make build provenance easier to adopt for package registries. If you remember, I mentioned on the server-side validation step, we currently check that the SLSA predicate matches what's in the Sigstore signing certificate. And this is a kind of roundabout way of making sure that that information hasn't been tampered with during build, and to get this standardized format that is interoperable. But I would love to explore if there's ways we could actually move this abstraction higher up. So could the CI/CD system actually provide a SLSA predicate that's signed as an ID token, and we can just stamp it into the certificate or something like this. And writing a Sigstore client from scratch is a huge undertaking. It's quite complex. There's a lot to get your head around. There's a lot that can go wrong. There's a lot of cryptography involved. So my hope is that there's already work underway to build out the Rust client, and hopefully we could maybe get to a point where that's a kind of core library that you can build your native language client on top of using bindings. Maybe we could use WebAssembly interfaces or something. That could be cool. And the thing that I haven't touched on much in this talk is we have provenance. We can verify that it was signed by Sigstore and NPM received a package, and we can get this information to users. But we haven't really done much to create more powerful verification policies around, like, okay, well, what is the expected signing identity or source identity for a given package? I think with things like trusted publishing, you could actually bind that to the provenance. So that could be a policy on the registry side, where the registry says, oh, your provenance has to match the trusted publisher. You can maybe say you have to publish with provenance for this package. And that can then be the public proof where the package came from. And then on the consumption side, consumers could potentially build policies, maybe some kind of trust on first install type thing where you build a policy based on where things came from and then warn if it changes. Cool. I think that's it for my talk. Thank you. And I have a little link here at github.com/npm/provenance for more information about how npm provenance works, and also a little kind of step-by-step code for how to generate provenance without npm, but in the same format.
We have time for one question.
Thank you. So it feels to me like the build provenance is generated by the CI system, and as a builder developer, I want to generate SBOMs for the things I built. Do you see that extending in naturally? Like Sigstore should also sign the the SBOM for me, so I can upload that to the registry as well. Does that fit in with the future plans, or is that a nearby thing?
Definitely. I mean, we've already, so Brian DeHamer, who wrote the Sigstore JavaScript client, also added support for SBOM generation in NPM. And that spits out an SBOM, but it's not signed. So we've already kind of thinking of like, oh, feels kind of natural to just sign it.
Right.
And bind it to the source code where it actually was generated, because that's a big problem with SBOMs. Like you could upload it, but then you don't even know where it came from.
The build system.
And then we can maybe even use that information to then kind of verify that the SBOM is true by reproducing the build later and checking that or reinstalling it and verifying that the same dependencies were installed.
Thank you.
So I think definitely, yes.
That's all the time we have for questions right now. Thanks again to our speaker.
Thanks.